Hello everyone, welcome to this online video series on Quiver Representations. My name is Simeon. I'm a third-year bachelor student of mathematics here at KU Leuven, and at our university we have to write a report to finish our degree on a subject of our choosing. I landed on Quiver Representations, being generally quite interested in algebraic stuff, but I found the video material available online quite lacking, and so after having worked on this for a semester, I thought I'd spread the love and teach you a bit about this beautiful subject, because it really is something that has caught my attention as being a really cool bit of mathematics that I really didn't know much about at all. So I'll be leaving some links to better books and other resources that you can check out in the description. Two books that I really do want to highlight right now are Quiver Representations by Ralf Schiffler. Very accessibly written. It really has helped me quite a lot to actually understand this stuff. And then there's a book affectionately called the Blue Book, because its full title is something like Elements of the Representation Theory of Associative Algebras, Volume 1, Techniques of Representation Theory, which is, as you can imagine, a mouthful. It's written by three authors, Ibrahim Assem, Daniel Simson, and Andzrej Skowroński. My apologies for butchering the name. That's also it's a very dense text, but it really does cover a lot. It's a very deep text. I won't be going anywhere near that level of detail, neither in this video nor probably the entire series. But today I thought I'd just cover some basic definitions. I am, to be honest, I don't really know what subjects I will be covering, partly because I'm making this video series as an excuse to not study for my other courses. It's like the middle of exam season for me right now, and I a lot of love to complex analysis, but I'd really rather be doing algebra at the moment, and we didn't have any algebra courses this semester, which is a real pity. In any case, so I'll just cover some basic definitions. I'll probably be talking about the thing that my report specifically focused on was the bounded derived category of representations of certain classes of quivers, specifically Dinkin quivers. I probably won't be going anywhere near that advanced of a thing, but I will probably be talking about path algebras, the link with module theory, projective modules, injective modules, and how those correspond to projective representation, injective representations. The representation type of certain quivers. I don't know. We'll see I'll see when we get there. But just for now, let's cover some very basic ground. Specifically, what is a quiver? If you have a background in discrete mathematics, the words directed multigraph might mean something to you. If they don't, that's fine also, because we use a slightly different formalism anyway. So a quiver is really a bunch of points called vertices, and then arrows between them. So we do, there is a directionality associated with these arrows. They're not just connections, they really do have a start and an end. And we represent that as follows. So we have some quiver Q, which is going to be a four tuple. The first two elements of the tuple are going to be sets, called Q0 and Q1 respectively. Q0 is the set of vertices, Q1 is the set of arrows. And then to know where these arrows start and end, we have two maps called S and T. They are both maps from Q1 to Q0. And they take an arrow in Q1 to its starting or its terminating vertex respectively. One very nice thing about quivers is you can visualize them very easily in a very evident way. So let's cook up an example here. So let's say we have, actually maybe I'll draw this a bit bigger. We have, let's say, 4 points, right? Actually maybe 5. We'll have 5 points. It's the Yuletide. It's around Christmas time where I am right now. Let's have some fun. Let's have some merriment. I'll label these 1 through 5 as follows. And then let's draw some arrows. I'll actually use a different color. So let's have some arrows. maybe one here. Now, something I do want to highlight is there's absolutely no requirement for these arrows to be unique in where they connect. Which what I mean by that is, we have this arrow here from 2 to 1. It's perfectly allowed for me to have another arrow from 2 to 1, which is properly distinct. Like it's a different arrow. There are certain definitions of graphs where you don't allow such behavior. Another thing that isn't allowed in some types of graphs, but is allowed here, is loops, right? So I could have a vertex 3 here, let's say, and then I can have an arrow that starts at 3 and also ends at 3, right? So these would have the same value for S and for T, this arrow. And also there's absolutely no requirement for the structure to be connected in the graph theoretical sense. So, I could have this vertex 5 just hanging around. Let's say it has a loop to itself. Why not? But that's absolutely allowed. In practice, we can decompose quivers into their connected components, and then those are easier to reason about, and then we can, there's some simplifications you can do, but this is the most general kind of thing you could have. And let's label these like alpha, beta. This would be gamma, I guess. Then delta, eta. I don't actually know what the next letters is, like zeta. That's not how you write that, but whatever. So yeah, that's a quiver. That's really all there is to it. Now, obviously, we're not just interested in quivers, but we're interested in representations of quivers. A representation, this is something that comes from the field of mathematics called representation theory. A representation is a way of taking some potentially very complicated mathematical object, like in this case a quiver, and finding a translation in some meaning-preserving way to the world of linear algebra. Why do we want to do this? Well, if you do study mathematics, you'll probably have had a linear algebra course, and you've noticed that, well, everything sort of clicks together very nicely. There's linear algebra is, in a sense, one of the only kinds of mathematics that we can really properly understand. I think there's a quote by, I believe, Wilhelm Stein, but I might be mistaken there, saying mathematics is the art of reducing everything to linear algebra, and that could really be seen as like the slogan of representation theory. That's all they care about. I'm being reductive here, but and so that's something that we want to do for quivers. Why do we want to do this, by the way? Well, in linear algebra, the idea is that intuition for mathematical objects is probably easier gained when they are in the easier context of linear algebra than in the potentially very wild and complex context of whatever original thing you were studying. And then by translating between these in a meaning-preserving way and being intentionally vague here, you can probably gain some insight and some intuition, which is nice. Now, in particular, how do we make this translation step? I'll switch back to white here. How do we make this translation for quivers? First thing we have to do is fix a field K, field in the algebraic sense. Throughout this video, I'll probably just be assuming that it's the complex numbers, because as fields go, the complex numbers are quite nice and quite fun to work with. Having just bashed complex analysis. So we have to have some field K, and then a representation of a quiver is formed by taking a K vector space, so in this case a complex vector space, for every vertex in our quiver, and then choosing linear maps between the corresponding vector spaces. That's our quiver there. A representation for this could look like the following, right? So let's say we choose C squared, the vector space, like you have R squared, right? The complex plane. And then we have, just say, a copy of C, another copy of C, maybe the zero space here, because those also exist, and then like C cubed. Why not, right? And then we'll have some linear maps between them. Again, I'll choose the green color. So alpha here, let's say that's projection onto the first coordinate. Then beta, let's say, is projection onto the second coordinate. Gamma, let's just say like multiplication by the constant 2. delta, well, we really have no choice here, right? Because we're going to the zero vector space, the trivial vector space. So there's only one possible map. For eta, we'll choose like the sum of the coordinates, and then for zeta, I don't know. It really doesn't matter here what I'm choosing, so I'll just take some random complex matrix and then, you know, be done with it. Whatever, it doesn't matter, right? This is a representation. Some notation that I'll be using throughout the series probably is something that's not quite standard in literature, but it is, in my opinion, very practical. Which is to say, if we call this whole representation M, right? So that's like the entire collection of, well, both the vector spaces and the maps between them. Then if I say like M subscript 2, what I mean by that is the vector space that the vertex 2 gets represented by in M. So in this case, that would be the you know, C squared here. And then if I say like M sub beta or something, I mean the linear map that that beta gets represented by. So in this case, it would be like this, you know, this map right here. That's not quite standard, but it's very practical to use that notation. Something to point out: there are certain representations or like sort of constructions that you can always give for any given quiver. One of them is the zero representation, which is not very interesting, but it does exist. It's just you set all vector spaces to the zero space, the trivial vector space, and then there's no room for choice even anymore as to what the maps are. They're just all the zero space, the zero map. Sorry. Slightly more interesting is the simple representations. So the simple representations are defined as follows. It's notated SI, where I stands for a vertex, so an element from Q0. Oh, that's not the rationals. It's also sometimes noted like S subscript I, which I find a bit confusing because, again, I use this notation of using a subscript for elements of the representation. Now this is defined as follows, right? So the jth space, right, where J stands again for let's do it like this, right? So I and J are elements of Q0. So the jth space of this simple representation at vertex I is going to be defined as follows. It's a single copy of the field K if I is equal to J, and just the zero space elsewhere. Now, what does this mean? In practice, the simple representation at some vertex I picks out a vertex I from the potentially infinitely many vertices that Q consists of, and then designates one as being the special one. Everywhere this representation will assign the zero space except for at that one specific point, right? The maps then are, well, we rarely even have any choice. Since, well, consider the situation where we have some arrow that starts in a vertex that isn't I. Well, then it starts from the zero space, and so it can only be the zero map. And conversely, consider an arrow that ends in a vertex that isn't I. Well, then it ends in the zero space, so it can also only be the zero map. The only exception is if we have an arrow that just happens to be a loop at our vertex I. And in that case, we choose the identity. So, you know, multiplication by 1 in particular. Just like for completeness, let me notate this properly. So A will be an element of Q1. It will be an arrow. And this is going to be the identity if and only if. So the starting vertex of A is equal to the terminating vertex of A, i.e. A is a loop. And that also happens to be at the vertex I, and everywhere else it's just 0. Notice that this last bit isn't even by choice. This is forced upon us. This is really the only thing where we had any choice. You could just as well say, you know, for these loops I want to define multiplication by 2 as the map there, but that's not really what we're about. That's also just not what the simple representation is. These representations are called simple because they, in a sense, capture all other representations, right? We can build other representations out of these. I'll probably show in the next video how direct sums of representations work and how indecomposability works. But suffice it to say, these simple representations really function as building blocks, in a sense. So let's actually take a slightly simpler quiver to demonstrate this with. I'll just, maybe let's do 4 vertices and then like 3 arrows like this. Again, I'll label these 1, 2, 3, 4, and then alpha, beta, and actually let's choose delta here because that arrow was called delta in the previous example. So if this is our quiver Q, then for example S of 2 would look like the following. Again, with the assumption that we are working over the field of the complex numbers here. And I don't even write anything next to these arrows because they have to be the zero map. So that's simple representations. The last thing I want to show for this video is morphisms of representations. That is to say, given 2 representations of the same quiver, how can I make sense of mapping between these representations? A subtle thing going on there is that we really are going to consider representations as one thing, one singular object, as opposed to really, being composed of smaller vector spaces and linear maps between them and whatever, which is a subtle shift, but it's something to be aware of. And in general, in algebra, a theme that you're going to find often is that if you want to map between these structures that are composed of smaller structures, then a good idea is to map pointwise between the smaller structures and then add some commutativity requirement. So what I mean by that is, let's take the simpler quiver example that I have just erased. So, vertex 1, vertex 2, vertex 3, vertex 4, and then we have alpha, beta, and delta. In this way, this is now going to be our quiver Q. I can come up with a few different representations for this, right? So let's have some representation M. We'll do nothing fancy here. Let's say this is going to be projection onto the first coordinate. This is going to be projection on the second coordinate. This is going to be like the sum of the 2 coordinates. And then if I have some representation N, and I'll really make it an easy case here where we just have 2 copies of the zero space, and this will be multiplication by 2, let's say. Okay, so 2 perfectly valid examples of quivers. Now the question becomes, okay, how do I map in a sensible way from N to N? Let's say that this map is called F, right? As I was just saying, we want to find pointwise maps in a sense that respect the smaller structure that we have going on, and then add some commutativity requirements. Pointwise in this case means, well, let's look at, for example, M sub 1 here and N sub 1 here. As I'm saying this out loud, I realize I should have chosen letters that sound more distinct than M and N. I hope you'll be able to follow along. So we'll have some pointwise maps going on here. That is to say, we have an F sub 1, which is going to be a map from this M1 to this N1, and likewise at all other vertices. So this will be F2, this will be F3, and this will be F4. F4, like this. We want these to respect the structure that these vector spaces have going on, i.e. they should be linear maps. So in particular, I'll write F1 as multiplication by the constant lambda. This is a map from C squared to C, so it will be a 2x1 matrix. Or well, actually no, 1 row 2 columns, so 1x2 matrix, with, let's say, mu and nu as entries. Why not? And notice that for F3 and F4 I have no choice, right? These have to be the zero map. Perfect. So that's something that you could choose, right? This is the most general pointwise map between all of the vector spaces of M and all of the vector spaces of N. And now I was talking about this commutativity requirement. What do I mean by that is, well, consider our quiver Q. There is a way of going from 2 to 1. right? Namely by way of this arrow alpha. If I want to like translate that into going via this morphism f, I have two ways of doing this. I want to like start here and end up here, right? But there are two ways of doing this. Let me actually choose a different color so it's like visually more distinct. Let's go for like, yeah, this is a nice color. So I want to go from here to here. I can either stay in M for a while and take M sub alpha and then go down using F sub 1, or I can go down immediately using F sub 2 and then stay in N and take N sub alpha. These are two different paths, as it were, within this bigger diagram to go from M sub 2. Oh, have I chosen black as, yeah, wow. So to go from C squared to C here, like from M sub 2 to N sub 1. And the commutativity requirement precisely states that it shouldn't matter. It should not make a difference whether you choose this path or this path. And algebraically we can capture this as follows, right? So this map after this map, which we will write as like lambda times the matrix 1, 0. Again, composition of linear maps corresponds to multiplying their corresponding matrices. This should be exactly equal to, well, doing this one here, so that's this 2, after mu nu, right? I'm writing over myself a bit here. So if we work this out, it turns out that lambda 0, this vector, should equal 2 mu and nu. And from this we can derive this set of equations, namely that lambda has to equal 2 times mu, and that nu has to equal 0. So in particular we can write 0 here, right? Okay, fantastic. Now, this is just one set of requirements, right? We have only really said anything about alpha having this property that it should commute, but we want this commutativity requirement everywhere. In particular, for every arrow A in our set of arrows, it should hold that if you first stay in M and take M sub A, and then follow that up by f of the terminating vertex of A. Now this composition should equal the composition where you first take f of the starting vertex of A, and then compose that by n sub A. So this is like the more general form of what we have just described. In particular for this quiver, let's quickly work it out actually. So for example, something you like to see when you're working with quiver representations and you want to like get into the nitty-gritty calculations, there's lots of zeros and lots of identity functions. Because, well, let's consider this square here, right? So you can either go like this or like this. Since this has to equal 0, this map, this composition in particular going across like this has to be the 0 map. So we know that f2 composed by whatever this map will be has to equal the 0 map. But fortunately it already does, because this is already the 0 map. So the commutativity requirement here for this arrow beta doesn't impose any additional restrictions on f2, because all of it is already taken care of, as it were, by this 0 map. I'm anthropomorphizing here a bit, but I hope you get the gist. And then let's see what's happening at delta. So this f2 followed by this 0 map has to equal this 1, 1 followed by this 0 map. Again, since the final step is the 0 map, whatever we do, right, is either here we're doing the 0 map or here we're doing the 0 map. So again, this imposes no additional requirements on f2. So in fact, this system is underdetermined, right? What I mean by that is we have some free choice in how in what f looks like. Now, in particular, as soon as we pick either a value for lambda or a value for mu, then the other one is fixed. So we have the choice of one complex number really, but that is still a choice, right? and in particular, this is something that you can what's a good word for it? Quantify, in a sense, using the space of morphisms between representations. And this is a proper space. It's a vector space. Well, actually, is it? Yes, it's a vector space. We denote it as follows. So we have hom of m comma n. This is just the space of morphisms from m to n. And in this case, it's isomorphic to, well, actually, I probably shouldn't have written this here. Let's just write it down here another time, just so I don't write over myself too much. So hom of n comma n is isomorphic to the complex numbers, right? Because we have exactly the choice of one complex number, and then all of the rest is fully determined by just this commutativity requirement. It is very often the case that hom of m and n is not the same as hom of n and m, right? So this is not symmetric in that sense, and we shouldn't really expect it to, right? Like, there's no reason to assume that if I have two groups, then I can possibly map in more ways from one to the other and from the other to the one. So that's something to keep in mind here. The last thing I will say is that a morphism that always exists is the zero morphism, which just assigns, which would be here like picking 0 for lambda, which would force mu to be 0, and then all of the maps are just the zero maps. That always exists. By exists, I mean that choice will always yield a valid morphism of representations, but it's not particularly interesting because it always exists. And so we don't really consider it, well, it's a valid morphism, but we'll often leave it out for simplicity. And that's probably where I want to end this video. Thank you for watching. I hope you have learned something from it. I hope you'll stay tuned for the future episodes where we'll do slightly more interesting stuff.